everyone. Contest 10 today. I tried to make it easier than usual, but okay, last problem is actually too hard probably. So maybe I missed some easy solution for the last problem, but my solution is a little bit too hard. It would be not that hard if I would use prepared segment tree, because I decided to use it segment tree here, and for some reason I decide I will just write it from scratch. Okay, just for educational purposes, to educate myself, yeah, to not forget how to do it. And it took some time. If I use just pre-written segment tree, it would be much easier, I think. Problem G is fine. Yes, problem G is cool. I would read your solutions, actually. I'm interested. So my solution doesn't use any specific formulas, just normal calculations. No. Okay. No, I think no specific formulas used. Problems up to F are pretty simple. So problem F is fine also. Okay. Background components. I try to solve it. I try to solve it with very simple solution first, but then it turns out it is actually not that simple. So you need at least do something. Small string concatenation is interesting problem. I'm actually not, I don't know how to prove it actually. So we will talk about it. Okay, so let's go. Problem 1, very simple problem, but again, today it's technical problem, so you just need to carefully implement what's going on. So you have two sets of digits. You need to find smallest number which contain at least one digit from each of two sets. Again, if these two sets intersect, then we have one digit number. If these sets do not intersect, we can pick one digit from one set, one digit from another set, and just combine them. Yeah. So okay, I actually implemented it in a very strange way. I'm not sure why. It's like the first thing how I imagined this, so that's how I implement. So I put them in a set. So I put one digits in one set, these digits to another set. Here I check if there is one digit which belongs to both sets, then I just output this digit. If not, I would make two loops. So I will make loops. It's not how you implement it actually. You can just take minimal digit from each set, but okay. I usually on easier problem, sometimes I solve them without much usage of the brain. So I just disable the brain and just print the easiest code which I first come to my mind. So okay, not the best code, not very proud of it. It works, but it's just not great. Okay, spend a lot of time to submit. Let's look how you solved it. Does anyone solve it in a very beautiful way? No, something like this. Okay. Yes. So you also put them to the sets. Okay, like this. Okay, you don't need to iterate over all digits. You iterate digits of one set and check if it contains another set. And you iterate them in increasing order because sets are sorted in C++. Okay, if not, you take minimal of here, or vice versa. And take minimum of all these two. Yeah, that looks much easier than mine, but okay, it's first problem again. You don't need to think about in the first problem, usually. Sometimes you do. Second problem. Okay, so we have some array. We can change the signs of the elements exactly k times. So the trick is you need to do it exactly k times. Yeah. So you kind of wanna change signs of the negative elements and the maximal possible negative elements. And if you have not enough negative elements, then you just switch one element back and forth. And if k is odd, then at some point you need to change it odd number of times so it stays negative in the end. And you just pick the minimal element and make it negative. That's basically the whole idea. Here I think a lot what is the easiest way to do it. For a long time actually I think. Surprise me sometimes how long do I think, because when you're in the process you don't realize how much do you spend of just thinking about stuff. Here we just it also makes sense. Yes, you can always just put the numbers in a set, just pick the smallest number and change the sign. Also should work, yes. So I decided to do it like this. So I just take all numbers in increasing order and see if number is negative and I have some more operations, just apply the operation. And in the end, I will check if I have some extra operations left. Here you see, and if case odd, then I need to invert the smallest number. So I make all numbers non-negative. Yeah, I take the smallest non-negative number and flip it, and just calculate the sum. Yeah. Again, many ways to carefully implement this. So again, we have two implementation problems now. Okay, first is strict just implementation. Here you need to think a little, but then just implementation. Yeah. Oh, we would have more implementation problems soon. I remembered. I remember what happened next. Problem C is also mostly implementational, but it's okay. It's more, I would say, mathematical problem. Problem C. We need to split number n into some composite summands. Okay, so here I'm just thinking, what composite numbers do I have? So we want to maximize number of summands. So it kind of makes sense to use small composite number, yes? And I just check which are smallest possible composite numbers. So I found number 4. Yeah, number 4 is the smallest possible composite number. It just means any number divisible by 4, you can split into just 4s. Yeah. Then I found number 6. Okay, now I have more possibilities. Yeah. So I can make 6 and plus some 4. So if number is even, yeah, and it is at least 6, I can make 6 and plus 4, 4, 4, 4, 4. Yeah. And again, this will be the maximal possible number of summands for this number. And so now I solve problem for all even numbers. You see, for any even number, I can use only 6 and 4 and make this number. So any number starting from 4, I can solve. Yeah. Now we just need to make sure we solve for odd numbers as well. So for odd numbers, we need to find some odd composite number, and smallest odd composite number is 9. Yes. So if you have composite number, you need to take at least 9. Yeah. So after you take 9, you are left with something like some even number. Yeah. And for even numbers, we already know how to solve. I thought a little if I need numbers more than 9, but the next composite number is like 9 is composite, like 11 is prime, 13 is prime, 15. Okay, you definitely don't need to use 15. Yes, instead of 15, you can make 9 and 6. So that's it. So you only need these 3 numbers, and you just compose. Then, okay, there are multiple ways to solve this problem. I just solve it by carefully taking care of all the cases. There are not that many cases here, so I decide I will just track them one by one. Maybe not the best solution, but you'll see. Okay. Here I think where to start. Okay, I decided to start with the simplest solution. So if number is divisible by 4, I just split it into 4, 4, 4, 4, 4, and number of elements will be n over 4. Now, if n is divisible by 2, yeah, then it must be 6 plus 4, 4, 4, 4, 4. Yeah, yeah. If it is at least 6, then the number will be this. If not, then it's impossible. So if not, it means just number equals 2. Yeah. So here is just number equals 2. Okay. So we get rid of all even numbers. So now the number is odd. Now number is odd. So we need to use number 9. So I just check if my number is less than 9. Then it's impossible. And if not, I remove this 9, and then I'm again solving the same case as here. So I decide I just copy this code. Not the best way to implement this, but again, I try to solve it in contest mode, like I usually do it in the contest. So if I do it in a slow way, just okay, that basically I solve problems in 2 different modes. Sometimes I solve problem as, for example, when I prepare the problem, I carefully implement solution. I want to write it as clear as possible. I want to write a nice code and so on. But during the contest, I implemented it in contest mode. So I just minimize the time I spent implementing this solution. So I decided if you just copy this code here, it will not hurt. So if the problem is a little bit more complicated, I would probably consider simplifying this code, because I just copied these two parts. Not a great code style, right? So if I have mistake here, I copied mistake twice. Okay, that's it. That's problem C. My implementation is short and here. So let's look at your implementation. That one is you, right? Yeah, it's a little bit easier. Yes, we have a little bit less number of cases. So if x equals 2, and or if it is the small, okay, small odd number, so if it's okay, divide it and then divide this. Okay, makes sense. So you get rid of all cases when it's impossible. Then you track case when you have odd number, and then you just in all other cases you have just x over 4. Okay, not bad, not bad, not bad. Let's go next. Problem D. Problem D, I'm not sure what's problem, why this problem is here. But again, it's okay problem, it just looks strange. So what we need to do, we need to find maximal number which is not divisible by any number from 2 to p. Yeah. So we have maximal number not greater than y, which is not divisible by any number from 2 to p. So I was just first I was thinking what the hell happening. And then said why I can just pick the big prime number. I just said I can. Yeah. So you always can pick a large prime number. It will not be divisible by any small number. And actually there are a lot of prime numbers. So actually you probably have prime number pretty close to your upper bound. Yeah. So yes, the problem is you may pick number greater than the prime number. So you not specifically need to pick some prime number. You can pick non-prime number. Just make it not divisible by any number to p. Yeah. So what I will do, I will just check all possible numbers and try if this number is good or not, starting from highest to lowest. And again, pretty soon I will find prime number, and prime number will always be good. Yeah. That's the plan. So I will just check all the numbers in decreasing order. If the number is good, I pick it. If it's bad, I skip it. Yes. Because there are a lot of prime numbers, pretty soon I will pick a prime number. Prime number is always good. So I don't need to check that many numbers here. Yes, here it must be not greater than 2, here must be greater than p. A lot of mistakes here, yeah. So I will fix them. Okay, that must be why. Here I think, okay, 3 number is prime, yes, but it's not good because it is divisible by 3. Yeah. So you don't need to check numbers greater than p. Yeah, like this. That's it. That's basically the whole code. So I just take all numbers in decreasing order and check if this number is good or bad. To check if number is good or bad, I check all the divisors up to p or up to square root. Yeah. If I check all the divisors here and none of them divides x, then x is a good number. So it's either not divisible by any number in this region, or it's prime. If it's not divisible by any number up to square root of x, then it is prime. Yes, that's it. So that's I believe I made mistake only in f today. Problem f is scary. Not scary, just tricky, I would say. Yeah. So that's it. That's it. Okay, let's move next. Problem E. Well, problem E is actually interesting. I'm not sure how to prove it. So I just know the fact that you can just sort all the strings in specific order. So again, here I actually forgot how to sort elements in more than C++. Yeah. So you can do it like this. You can sort and put a comparator here. I'm not C++ expert again. Yeah. So the idea is you can sort the strings with this comparator and it will give you the desired result. Again, what this comparator does, it tries to change the order of the strings. If it's lexically smaller, when you change it, you say this string is less than this. No, obviously, if you have optimal string, you cannot change the order of any two consecutive strings. Yeah. So if you change the order of consecutive strings, the result must be greater or equal. Yes, because you have the minimal possible. Yeah. Again, let me draw some picture for you. Oh, that's spoiler. So in the result, you have some string in some order. Yeah. And if you pick two consecutive strings like this and swap them, yeah, then this resulting string must be greater or equal than this resulting string. Yes. So for these two strings, let's say alpha and theta. Yeah. So alpha theta must be less or equal than theta. Yeah. And it works for any two consecutive strings. And it turns out this property actually make order on strings. This is something I actually don't remember how to prove. So this is a good comparator. No, again, it's kind of like unsymmetrical, it's boring. Interesting fact that it is transitive. Yeah. So if we have some alpha beta, let's recall beta alpha, and we have beta gamma less or equal than gamma beta, then we have alpha gamma less or equal than gamma alpha. Yeah. So this comparator is transitive. I'm actually not sure how to prove this. Maybe you just look at these strings and just prove it. Yes. So you have alpha. Let's say not less or equal. Let's say strictly less for simplicity. So there are two cases. You either have this common prefix and then you have some character x, y, or you have the same common prefix, but you have this character here, yeah? And then you have beta gamma less than beta. Have beta, and here we have gamma. So this is less than this. So again, you have some common prefix here, and here we have some letter. Okay, let's say A, and here we have letter B. And just prove that this alpha is less than equal, because so if this common prefix is inside alpha, then here you have this prefix less than this prefix. So that's true. So just alpha will be less than gamma. And if it, so I believe you just trick several cases where this common prefix ends, and just see that in all cases you have this true. Maybe there is easy proof for this. I have no idea actually. I have no idea. I remember it's just a magical knowledge in my brain. So if you do it like this, you have a good comparator. It's interesting. I think it's a classical problem. Let's find it. Smallest string concatenation. Oh, smallest string concatenation. Oh, that's not, that's fun. Okay, I like this proof. So you can prove it by looking at numbers as by strings as numbers. Okay, so every string you can consider as a number base 26. Okay, and then you have something like this. That's nice. I didn't know about this proof. I like it. But the problem is very classical, I believe. So when it's 10 years ago, okay. I believe I knew this problem even before this. So I knew this problem when I was in university, and it was more than 10 years ago. So let's say it's just classical problem of strings. So if you didn't know this before, that means you just learned something new today. It's good. I believe your solution. I believe all your solutions works in the same way. Yeah, it's kind of hard to invent something new here. Good. So okay, so that's it. So if you didn't know this property before, so you just learned something new. If you just guessed this property during the contest, that's also good. So sometimes you just need to trust your intuition. So you just think that some property looks like it's true. So instead of proving it, you just try if it works or not. Here it was easy, yeah. So it's just not that much code to implement. So you implement like 5 lines of code, and it either works or not. Yeah. You can write a stress test if you want to be sure, but I decided just to submit. Okay, so that's problem E. That's problem E. You need to prove transitivity to prove that sorting works. Yeah. So for sorting algorithm to work, you need to have a proper order relation between elements. Yeah. So it must be transitive. So if it's not transitive, the sorting will not work. Here I accidentally picked problem G instead of problem F. Yeah. I opened problem G, and for some time I actually thought, what the hell happened? Why it's so difficult? So it didn't supposed to have that difficult problem in position F. Yeah. Sorry. Okay, so here I'm just reading the numbers. So I decided to read them as a vector of digits, like I normally do. Okay, you can store them in strings, but I usually do it like this. So I put them to vectors of ints, just so I don't accidentally do something stupid in the middle. Okay, here okay, here actually I will change it multiple times during this during this video because sometimes you want to look digits from left to right, sometimes you do from right to left. Usually you're doing from right to left, from smallest digit to largest digit. But here is actually do it in both directions multiple times. So I will change this string multiple times actually. Yep. So what we need to calculate? We need to calculate basically this simple formula. We call it b minus 1 multiplied by b power n minus 1 modulo c. Yeah, that's what's written in this problem statement. So if you just read this problem statement, that's what you need to calculate. The only problem is that numbers b and n are huge. So you have huge number b, huge number n. Huge number b is not a problem. Yeah, you just take b modulo c, and that's it. You have small number b. Huge number n is larger problem. Yeah, no, because it is power. So you need to calculate. Yeah, so you need to calculate some number, power, some huge number, modulo c. Yes, I believe it can be done. We will read your solution. Some of you solved it using Euler theorem. I didn't know. I actually don't know how to solve it using Euler theorem. Well, I maybe know, but it's not that easy. Because for Euler theorem, you need the number to be co-prime with c, and my c may be not prime. Yeah. So if the model is prime, it's kind of easy. Yeah. So you take this model, you take this power model c minus 1, and it's it. Yeah. Because all the powers are cyclic, and the period equals to p minus 1. When the number is not prime, you still have kind of cycle of size Euler function of c, but number should be co-prime, not? Or you can just do it, or it doesn't matter. I know that any number, so I know that any number power phi of c should be equal 1 modulo c if a is coprime with c. But if not coprime, strange things may happen, no? Cycle tail in the beginning. Okay, I'm not sure. Okay, I will read your solutions actually. So my solution doesn't use this because I decided. So I haven't because it's not prime. I was not sure how to do it. You can probably do it like this. So you can factorize c, solve the problem for any prime factor, for all prime factors, and then combine the result by Chinese theorem. I consider doing this at some point, but then decide I will just calculate b power n minus 1. You can calculate power in log n time, yes, and log n is small, it's like million, yeah. So I will just calculate this power like I do with binary exponentiation, yeah. Yes, which you can simplify it by minus 1. It actually makes sense. Okay. So it may be much easier problem than I thought. Okay, but okay. How I did solve? How did I solve this problem? I just calculate b power n using the same algorithm as I use in binary exponentiation. Here it's not binary. Here it's like decimal exponentiation, but the idea is the same. Okay, so here I calculate number b modulo c. Just to take it digit by digit, calculate modulo c. Okay. What b? Okay, I was thinking something. Okay, here you have to make n minus 1. Yeah. So here I'm doing minus 1. Just take digit by digit and decrease by 1. If I have 0, I make 9 and go to the next digit. So here is how I usually write minus 1 in long integers. Yes, I'm just procrastinating. I'm trying to think something more fun than just to do this. Okay, the idea I implement here is like this. So if I have, it's basically the same. So if you think about binary exponentiation, you basically split the number into bits, and for every every 1 bit, you kind of multiply the result by your number power 2 something, yeah. So here I kind of do it like this. So I split my number into digits and calculate result is b power this, multiply b power this by b power this, yeah. Now each of this number is, I need to calculate b power 10, b power 100, yeah. So I go to 1 power to the next power by taking 10th power of this number. That's the idea. Okay. So I calculate b. So yeah, let me write. What is the idea? Again, you need to calculate b power, okay, 239, yeah. So we split it into b power 200 multiplied by b power 30 multiplied by b power 9, yeah. And then I will just write it like this. I will take b power 100 square multiplied by b power 10 power 3 multiplied by b power 1 power 9, yeah. So I will calculate these numbers easily. Yes, yes, just go from here to here. Every time you just take 10th power of this number. Then for each of this number, I will calculate this power. Yeah. And then combine the result. That's the idea. Okay, let's just need to implement this. So I take digits of number n from lowest to largest. Okay. I'll just combine this number n. So just each number. So I take power d. You see, I just do it simple loop. It's up to 10, no more than 10 iterations here. Yeah. So I take this. So bb is current power of b. I take it to the degree d. D is my digit. Yeah. So this is something I need to add to result. Just add it to the result. I would simplify it. Normally, I would take my pre-written code for modular arithmetics. Here, I decide I will just do it like this. So after every operation, I calculate modulo c. Looks ugly. You normally do it in not like this. Okay, and here you need to move to the next power of so to take it to the 10th power, like this. No, like this. So I take my current power of b, take it to power d, add it to the result, and then take it to the 10th power, go to the next digit. That's it. Okay, while I'm compiling, what did I forget? It will get wrong answer. Why? What did I forget? Who is the most? Oop, oop, oop. Don't you see? Okay. It will get wrong answer test 3. Can you find the mistake? Stupid mistake, actually. Test 3 is n equals 1. I don't know. Actually forgot to make this b minus 1. So the formula is b power n minus 1 multiplied by b minus 1. In both cases, b equals 2, so you don't need to multiply by b minus 1. Yeah. That's all. That's the mistake. So that's basically the whole code here, you see. So here is how you calculate powers if you have number in decimal, not in binary. If you have it in binary, you can take bit by bit. Every time you take square and multiply square, multiply. And if you have number in decimal, you do basically the same, but you have 10th power and calculate here. So it's slower than in binary, but still works. Let's look at your solution. So you can just calculate Euler function and just what? That's minus 1, yes. Okay, low up minus low. What? It's b power n minus b power n minus 1. Makes sense. So that's b power n. Okay. So it's 2 strings and number. Okay, these numbers just take modulo c. You calculate phi of c. This looks like cheating. What? So if b is small, you just do it like this. But if b is large, then you can take it modulo phi.
It's to consider that part where if they aren't co-prime, then there is a small tail at the beginning which doesn't follow the cyclic property. I already told that I did not do it myself, so
it's fun. It's cool trick, actually. You need to learn it for future. So you can you can take it modulo phi even if it's not coprime because of reasons. Okay, but if you just consider small cases, okay. So for large values you can take modulo phi of n even if they're not coprime. That's interesting. I make p plus. Okay, so it's the whole phi plus something else. Okay, got it. Okay, got it. So after I make phi iterations, you go to the cycle. So after that, you have cycle, which is a multiple of which is factor of phi. Okay, cool. Now I learned something new today. Okay, here are two solutions for problem G. You either use the Euler formula or you can use tricks like this when you calculate power using some binary exponentiation, just not modulo 2, but modulo 10, yeah, base 10. Okay, now let's go to problem F. Problem F, you can, so I actually looked at the constraints and thought again, so it's 2 power, 10 power 4, 10 power 4. It should be nice. So if I calculate k by m, maybe if I use just DFS and not the, okay, so I actually, my solution works not in linear time, so it works in nm multiplied by disjoint set union time, so it's a little bit, okay, and you just use DFS, it should be a little bit faster. Okay, so I decide I will do it like this. So yeah, like this. So I just take all the edges and just unite them in disjoint set union like I usually do. Yeah, here I make normal implementation of it. I usually implement very simple way, just like this. So I make the path compression heuristic. So here is it. So I just implement path compression and that's it. And usually just fast enough for any problem. And here I calculate number of components. So if p of I equals I, it means it is a root of its component. Yeah. So I calculate number of roots in my structure. It's just number of components. So I thought it will just work actually. Yeah. But then I got time limit test 556. Yeah. But you got it working. Yes. Let me see. Which F. No, not you. That you. You have this you also. It's interesting. You also have size heuristics, but it shouldn't be that different, no? It's basically almost the same solution. You take these elements, just take this element, and it fits. Yes. So how? What is the maximal time here? I see. Okay. So it's close to time limit, but still fast enough. Is it that different if I make? I normally think that it shouldn't be that different if I make size heuristics. Let me check. Let's check. Precision. Let's say if so I x, so if it is greater Like this. Compile, yes. Yeah, that's completely the same as my code. No? Okay, again, it's close to time. Okay. Okay, so it's actually speed ups. So solution little. That's interesting. I think they made specific tests just to break this implementation of DSU, because normally if you have some random problem and you don't have tests specifically against the DSU, you will not have problems like this. So I think they actually did some tests to make DSU work slow. Interesting. So again, even without the size heuristics, you have log n worst case time complexity, yes. But with size heuristics, you actually have it faster than log n, because factor that is problem. Yes, nice. Again, I learned a lot of new things again. But I decided to make it like so. I decided to just speed up solution asymptotically. So I will just change the solution to work much faster, not just try to fit it into time limit. So what I did, I actually nice trick. So when you think about think on connected components, you don't need that many edges actually. Yeah, so you see that number of vertices is small and number of edges is large. Yeah, so you don't need that many edges to connect this small number of nodes. So actually you have at most n-1 interesting edges, which connect something. All other edges are just garbage. They connect a vertex they are already connected. So you can go from left to right and check if you add this edge and it connects some new components. And if it connects already connected components, you can just skip it. This edge is not interesting. Yeah. So what I will do, I will make array of only interesting edges, which actually can connect some components. I will do it left to right, right to left. So I will have at most 2n components. Yeah. So I will have at most 1,000 different interesting edges. So it will speed up solution 10 times. It probably will work. Okay, so let's too slow. Okay, well here. So here I'm finding all interesting edges. You see? So I go left to right and see if I join some connect components, then I add this edge. Then reset DSU, go from right to left, and again, if edge connects new connect components, connect some disconnected components, then I add it. And then, so I will add at most n edges right, left to right, at most n edges right to left. That's it. So I have 2n interesting edges. And so in this loop, I only need to check interesting edges, not all of them, but only interesting. Yeah, that's it. So it will speed up solution like 10 times. Okay, I skip. So how fast is it now? My submissions. You see, it's just half a second. Yeah. Is that a proof? Proof is easy again. So what I just erased all the edges which are not interesting. So what we do? So what we do in this problem? We take some edges from the beginning and take some edges from the end. Yeah, we take all these edges, combine them, see how many connect components. Yeah. So if I have edge E here somewhere in the middle, and if I go from left to right, this edge, okay, let's say some edge UV. Yeah. So I go left to right. If I have this UV, if this node already connected before, so before I added this edge, they are already connected. So this edge doesn't change anything. Yeah. So you can just skip this edge, then do not consider it. And the same from right to left. Yeah. So the idea is just to drop all the edges which do not change connectivity structure. That's it. Okay, and let's go to the final problem. Final problem to get this. Okay, so okay, I didn't write that one. Let's stop actually. It's not fun to watch how I implement segment 3 for an hour. So what is the idea for the last problem? I think it can be solved in many different ways. What I did in this problem, let's open the problem H. So, okay, the first important idea I had in this problem that number of edges in this graph. So you consider it as a graph, yeah. So if you can make a flow from one panel to another panel, yes, from one panel to another, let's draw an edge from here to here, yeah. Okay, let's draw some example. Like this, two, and bottom panel. I just draw this example, yeah. So if you just consider each panel as a vertex, yeah, and then and then just draw edges if you can push flow from here to here. I can push flow here or here, and I can push flow here, 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 something like this, yeah. Let's add one more panel to make it more interesting. So we have some graph. Yeah, so graph of how can you push the flow, from which panel to which panel you can push the flow. And the observation is that this graph is actually small. Number of edges is linear. So M is. Why is it true? Because graph is kind of planar, you see. So you cannot make intersections because of this strange property, So you can only push the flow if you can plot flow in this region if you don't have anything intersecting this part. So you can push flow if whole this region is empty. Yeah. So if you just draw these edges as rectangles, you have some non-intersecting structure. So basically you have some planar graph. Planar graphs are linear. Yeah, again, this just interesting thing to keep in mind that if you have some planar structure, then probably it has some linear number of edges. Okay, so what I'm trying to do, I will just build this graph explicitly, just build all these transitions, just where I can push the flow from where, and then run normal dynamic programming over this graph. Yeah, that's the idea. The only problem is how to build this graph, and I will build it using sweep line technique. Again, it looks like a sweep line problem, yes. So I will do it using sweep line technique. I will do it like this. I will go left to right. So if I have two panels and I can push the flow, I just need to check like this. I just need to check that this region is empty. Yeah. So I will do it like this. I will go left to right with sweep line. When I find this point, so one of the segments ends, I will find the closest segment to the left, which is not ended yet. Yeah. And try to check if this region is empty. Yeah. To check if this region is empty, I will remember for each x coordinate, I will remember the maximal point I have in this x coordinate. Yeah. So what I will need to do, I will need to check that in this segment, so this is left, all values are less or equal than L. Yeah? So if all values on this segment, these values, are less or equal than L, then these panels will not interrupt this flow from here to here. Okay, hope it's clear. So I need a segment tree, yeah, which counts minimum on a segment or maximum on a segment. Yeah. So for each y coordinate, okay, it's y coordinate. For each y coordinate, I find the rightmost point of the segment which I have in this y coordinate. Then for this segment of y coordinates, I need to find the rightmost segment. So if this segment is somewhere here, then this panel will interrupt this flow. Yeah. So I just need to check that maximum on this segment is less or equal than L. If it is less or equal than L, it means all these segments are below this L. So this rectangle is empty. Okay. So that's how I did this. Maybe there is much easier solution actually. Okay, let's read my solution and then find what is the intended solution. I think it may be much easier. So again, I decided to implement segment tree from scratch. Not the best decision in my life. So I implemented this amount of code. Let's read it. Let's read it. So I have normal segment tree for maximums. Yeah. So this operation puts value in a tree, just normal tree. I just go down. When I reach the leaf, I put this value. Then I go backwards. When I finish the recursion, I recalculate the value. Yeah, just normal operation of setting value in a segment tree. Can you try sliding window? I'm not sure. Probably some. I believe probably some easier way to. There is easier way to do what I just done. And sure, I was thinking about using some set or something like this, but then I still need this maximum. So I decided, okay, if I can solve it using segment tree, I would solve it using segment tree. Okay. Okay, it's not the craziest data structure as segment tree. Yeah. So if you can solve something using data structure you're confident you can implement, just do it. Okay. So this operation finds the maximum. I put pair of value and index because I need to remember the index of this panel. So I need to remember which panel I hit. These operations I use to find the next panel. So I find the next panel which is on the same level as me. So again, to find this panel, also I need to find panel above me. This panel. This panel I also need to find. Yeah. So I'll find the closest value above and below me, which ends after me. So these values. So to find these two positions, I have these two functions. It will find the closest value to the left, which is greater or equal than v, and closer value to the left, to the right, greater or equal than me. Just normal segment tree operations. Actually, I have a full lecture again about segment trees. If you're not confident in segment trees, just go there and try to solve problems about segment trees. Now, imagine you have segment tree. Then, so that's the solution. So I take all my panels, add two more panels, top and bottom panel. Yeah. Compress coordinates. So I take all the heights, all this array H, and compress coordinates. Then I push the events. So for each segment, I have two events. When I see left border, when I see right border. Here is the type of the event. I want first to finish all the segment, then to start all the segment. Yeah. So finishing event will have ID 1, and starting will have ID 2. So I first consider all these events and then consider all these events. Yeah. Here I just build a segment tree from scratch again. Here, so that's the sweep line. So I go left to right. When I see the start of the segment, I just put the value to my segment tree. Yeah, that's what's happening. So every time I go left to right, so when my sweep line touches the left part of the segment, I put this value to my segment tree. Yeah. So every time I here, I know that I have a panel which sticks up to this point. Yeah. When I see the right point here, when I see the right point, I will, so this panel is I, so this panel will be J. Yeah. So I find the closest panel which sticks at least to my point, then find the intersection, find the maximum on the segment, this maximum, yeah, and check if it is to the left for this intersection. If it is true, then I can push flow from there to there, yeah. So I push this flow and add this edge to my graph. And then I do the same to the to this point again. This is also J. Yeah. So I find the closest element to the right. Again, find the intersection. Calculate maximum. Check if it's not. So check if this maximum is to the left from the intersection. If it is, then I can push flow from there. Yeah. Okay. So if they intersect, then I can push flow here. No, that's basically it. So consider this case, consider this case. You can probably, oh no. I think you can probably leave only one of these cases and just, it's harder to do it. So I prefer to do it like this. Okay, in the end, I will just call normal DFS. So this DFS just to calculate the okay, the path. It's dynamic programming basically. So it does topological sorting plus dynamic programming. Yeah. So, or you can think about a dynamic programming with memorization. Yeah. So here I will take all the edges and check if it is maximum of this edge and minimum of this flow and DFS of this edge. So it's just dynamic programming here, but over the topological sorting. You can do it in two steps. You can make topological sorting and then dynamic programming. I usually prefer to do it like in a single recursive function like this. Okay, not easy because it's like almost 140 lines of code. Maybe I overcomplicate things. Did anyone? Oh, yeah, you solved it. It's not your solution. You're not tricking me. Okay, it doesn't look much easier than mine. But no segment trees. Okay, you just use sets, yes? I can't read this part. So it goes, so sweep line in other directions, sweep line by age. Maybe easier. So I give sweep line not by x coordinate but by y coordinate. It maybe it makes sense actually. Okay, let's think about it. So if you take segments from a so you take the segment. You need to check which segments you can push flow to. So you take segments You can kind of take all these segments, but you need to check if it's not obstructed by anything else. It's look overcomplicated. So we kind of need to track the segment if both ends of the segment are covered, then we can remove this segment. We can never push any flow in this segment. So we need to only care about segments which have at least one ends uncovered. It sounds scary, actually. It doesn't scare. So there must be a tutorial about this. Huh? It's division 1D actually, not easy problem at all. Again, I usually think in this club we have division 3 contest, but it's division 1 for D. It's hard problem. You can maintain last level, not only last level, you can push flow to some lower levels. Like you have this, then you have this. It's even partially covered, but then you have this, and from here you can push flow here. So I thought you can keep only non-covered panels, but it's actually not true. So you can keep panels which are so which have at least one end not covered. That's true. So, okay.
What if it's like a panel has both ends covered and then in the middle there is a panel below it?
Ah, even like this. Okay. Yes, if it's both covered, yeah. Yeah. But then you have this small panel here, you can still yeah. Even this doesn't work. Okay. Sweep like this, solve the task with bottom to top. Okay, hold the part of the segment visible from this file currently end. Okay, in the binary search tree. Let's apply to the segment is found. Want to find all the lower segments. We can direct flow into the segments. Okay, this trick I knew. Okay, makes sense. Let's look at your implementation. You have Java implementation. Oh, I just saw this solution somewhere. Yeah. Please do not cheat. That's not the contest when you need to cheat. Why you copy this solution? It doesn't make sense to cheat in this contest. It's not even. We don't have any prizes for solving these tasks. It's purely educational contest. So why do you cheat in educational contest? Doesn't make sense. Okay, let's read it once again. So again, what is the so what is the idea? So we can keep basically the profile. So we have some. So imagine you have some segments. So let's have segment 1, then I have segment 2. Let's have some long segment 1, then I have some segment 3. So I go top to bottom, and you can maintain a profile. So you can maintain a profile like this. So I have segment 2, then I have segment 1, then I have segment 3, then again I have segment 1, something like this. So you can maintain profile like this. And you can maintain these segments in set, so in binary search tree. So no, C++ set is a binary search tree in set, yeah. So you can maintain this ordered set of segments. Yeah. So it's like projection of these panels onto x-axis, yes? So when you add one another segment like this, so you have like segment 4, yeah? You can update this picture, yeah? So you take all the segments which you intersected, replace them if they're completely covered, and insert your segment 4 here, yeah? So after that you have segment 2, here you have segment 4, and here you have the rest of segment 1. Yeah. Okay, so you can update this set of segments when you add new segment. And you can update it just using brute force. Just take all the segments one by one and update. It's true because amortized time will be still linear. Linear number of operations, yeah? Because you increase number of segments by at most 1, and you remove no more than linear number of segments, yeah? Okay, now when you so let's just track these segments one by one, and for each of them check if we can push the full flow between these two panels. We can check if this intersection equal to the length of this segment. Yeah, that might be easier than mine, but still this construction scares me a lot. So again, what we're doing, we maintain this set, where is it? Sweep interpret. Okay, we have some extra segments to track all, to not have all the problem with border cases. Okay, why not? So this sweep is a set, I believe. Where is it? Yeah, it's a set of parts. Yeah, every part is basically a segment with some parameter f. We calculate flow on the go. Okay, so we don't build the graph. Okay, we do dynamic programming inside this thing, bottom to top. Why not? In that no, we calculate dynamic programming right inside this sweep line technique. You can build the graph and then calculate dynamic programming over this graph, or you can build dynamic programming just when you build the graph. Because we build it layer by layer, we just calculate in this order dynamic programming. I would say it's overcomplications, but it's much easier to build graph than calculate dynamic programming. But who am I to judge? Okay, so this basically operation does what we need to. So this part looks very complicated. So I need to take all. You need to consider all these segments, then remove them, add your new segment, and maybe trim this left and right segment. Okay, I believe this thing does what exactly that, but I don't know. It looks too scary. This calculates dynamic programming. This part I know. But where do you remove it? You just write from here to here. Okay. So just take the segment of the set and erase it as in one operation. Okay. I would just erase them one by one. I would just take these segments, process them, and erase them from the set one by one. That's how I usually do it. Okay. You take the whole segment and just cut it. Okay. Why not? Okay, I'm not sure if it's much easier than my code actually. Okay, it's shorter because you don't have this segment tree. But again, if you have pre-written segment tree, my solution is probably even easier than this. Okay, so that's it. Thank you for coming today. See you next week.